Well, Dixon, you just did my first slide. Thank you very much. One of the takeaways I wanted to give to you is that, yeah, I call myself a data scientist these days, but I'm really a software engineer at heart. And I came to data science over about a decade, the last decade or so. And maybe some of you are in the same boat. Maybe you're a software engineer that's maybe learning data science. Anybody kind of consider themselves a new data scientist or a learning data scientist? Okay, this one's for you. Because over time, I learned, every day I still learn things I don't know, or I didn't know. And today I wanted to introduce to you 3 of them that I think are particularly interesting. Despite my background, this talk is going to have nothing to do with Spark, nothing to do with Databricks, nothing to do with code. It's just a little bit of stats, and nothing more complicated than a linear regression, but I think some of these questions and answers might unsettle you if you thought you understood these things. I'm going to go ahead and tell you the answer. The unifying theme to all these problems is going to be causation. Now we hear correlation is not causation, which is correct, but it makes us think that we should stay away from causation. That causation is a scary thing that we want to avoid thinking about. And in fact, that's not the case. We need to reason about causation because that's how the world works and that's how our brains work. But what is it? If it's not correlation, if it's not something we can just compute from data, how does it relate to the data? When does it come in? Right, so let's get to some interesting problems here. Simple linear regression. This is a data set built into R called cars. It shows stopping distance versus speed for some car. When you can imagine let's assume there's a linear relationship there. Maybe it's a little, not quite linear, but let's assume it is. And we're told that to get this linear relationship between these 2 variables, we just run a linear regression. No problem, fit a linear model, and we get this best fit line. And if there's this linear relationship between speed and distance, well, there's a linear relationship between distance and speed. So I could regress one versus the other, or the other versus the one. And if I do that, I actually get 2 different lines. I don't get the same best fit line. Now, there's a good reason for it, of course, and I think most of you maybe even know why mathematically that's not true, why I get a different best fit line if I regress one variable versus the other. But if you don't know, I'll explain it in a minute too, but if you do know, think about why. Why do I prefer one interpretation over the other given this data? Which one is actually the best fit line? Because one of them has to be the best. They can't both be best. Think about that one. While you're thinking, let me introduce the next possibly unsettling question. Okay, some of you are going to recognize this example. If you haven't seen it, imagine that there is a treatment for kidney stones, treatment A, and there's another treatment B, and it's given to some patients that have small kidney stones and some that have large kidney stones, and we see how many patients recover from the kidney stones for each of these treatments. Something funny happens when you look at the data. Overall, treatment B has a higher success ratio. 83% of patients that were given treatment B recovered. But if you look just at small kidney stones or just at large kidney stones, treatment A is better. A higher percentage of the patients in those 2 cases, when broken down by kidney stone size, recovered with treatment A. Now this is a well-known instance of Simpson's paradox. This is the example taken straight from Wikipedia, in fact. And a lot of the times we talk about Simpson's paradox and say, well, isn't that funny? But of course, the real question is, well, which treatment is better? Obviously, one of them probably is, but which of them is it? Which is the right interpretation? And I'm even going to give you the answer to this because I want to ask a deeper question here. The traditional interpretation is, well, it's harder overall to treat large kidney stones, apparently. The success rate is lower overall. And if you look, treatment A is given more often to large kidney stones patients. So basically, treatment A is being given to more difficult cases than treatment B is. So yeah, treatment B seems to be better overall because it's having easier cases to deal with. Actually here, treatment A is better once we control for this confounding variable, which is kidney stone size. So if you knew that part, be proud of yourself, but let me change the example a little bit. Now let me change the medical story without changing the data. Let's say that treatment A both treatments change the pH of the patient's blood, the acidity of their blood for some reason. And now I get the same data, but I have a slightly different setup medically. are we sure that it's still valid to control for blood pH and conclude that actually, yeah, treatment A is still better or not? Now, if it's because I'm asking the question, you may pick up on the fact that maybe that's not true, but we'll come back to why that is. But isn't it interesting that, number one, with Simpson's paradox, we realize that we may reach the wrong conclusion if we control for the wrong variable. But what is the answer? And do we control for these variables or not? And when do we control and when do we not? Maybe that's a little unsettling if you've seen Simpson's paradox before and haven't thought it through all the way. My last example is also taken from a data set in R. It's called Empty Cars. It's a bunch of vital statistics for cars from the 1970s. And it's maybe not the best data set to show this, but it was the best example I could find from the easy built-in data sets in R. So if you plot two variables in this data set, number of carburetors and the axle ratio of cars, you find they're uncorrelated. Carburetors, for those that were born in the 70s or after, or the old version of fuel injectors. And sure enough, maybe there's not a good reason to expect that those two design features of cars are highly correlated. You could have a lot of carburetors and a low axle ratio or vice versa. Maybe they aren't that correlated, that's fine. But the weird thing is, if I actually break this data set into two and look at just the 6 and 8 cylinder engine cars and just the 4 cylinder engine cars, this trend reverses, and I get not just before I had this weak negative correlation, basically no correlation, and now I get on the one hand, a pretty reasonably strong positive correlation, and on the other side, a weak but clearly positive correlation. So how did this happen? So I looked at this data, and there was no correlation between these variables, and I split it in half, and in either half, the variables are correlated. Well, that's weird. Now, why? And if you can figure out why this is, because this is an example of Berkman's paradox, which is it? Are these variables actually correlated, or are they not? And why? So these were troubling, because I didn't know the answer immediately the first time I saw these. And these arise from pretty simple data situations. And the good news is there is an answer to each of these. And the answer in all cases, has to do with causation. Causation is actually really important. Although we need to be careful thinking about it and careful deciding that a data tells us that something is causally related to something else, we can sometimes conclude those things. And we have to, because that's how we think. In fact, when we go to look at all data to understand how maybe certain signals affect a user's propensity to churn, we're actually wanting to draw causal conclusions. If we were to make this offer to this user, then they would not churn. We want there to be causal relationships from the data. But the data doesn't necessarily itself have that causal information for us. In fact, data can sometimes be consistent with multiple causal explanations. And we have to have some mechanism for deciding which of those causal explanations is consistent with the data and which is the one we need to pick. Because that's often what we have to correctly make inferences about the future, about unseen data. So we do need causation, we just need to be careful about it. Right, so in the first example, the reason you get two best fit lines is when you regress variables one versus the other, you're either minimizing the square distances horizontally or vertically. That's why you get different lines. And I was tricky here, and I put the correct answer is really the one that's on its side here. Of course, stopping distance is a function of a car's speed and not the other way around. If I drive my car faster, my stopping distance increases. It's not quite that, because if my stopping distance is higher, my car goes faster. That doesn't make any sense. So there's only one of those two causal interpretations makes any sense. And this is the model. The distance is some linear function of speed plus Gaussian noise. That's the only one that makes any sense from what we know about how the real world works. So that's the correct interpretation, and that is the best fit line for this data. You might say that we might represent this causal model as so. Speed causes stopping distance. And this is a very, very simple graphical model that encodes that information, and not the other way around. And the only reason we were able to draw this conclusion is because we know how the world works. We know what makes common sense. And we can disambiguate between the two. It's not always so easy. These graphs can get more complicated quickly. In the example with the original example of Simpson's paradox, we had the treatment A was the better treatment because actually the explanation here, the medical explanation, is that large kidney stones are harder to treat, and this better treatment is given to the hard cases more often. And so the right thing to do is to control for that variable. And so this is the causal model we might draw for this situation. The size of the kidney stones has an effect on the outcome because larger kidney stones are hard to treat. And it also has an effect on the treatment. It actually influences the choice of treatment that the doctor makes in this case. And of course, the treatment itself affects the outcome. And for those of you that have looked at graphical models, looked at PGMs, probabilistic graphical models, you know that this is a confounding variable. And so in a sense, there's some influence flowing this way that we need to chop out by controlling for size. And that's the right thing to do if we really want to isolate the effect of treatment on outcome. So yes, treatment A is correct there because we controlled for kidney stone size. Now in that second example, we changed the setup here a bit so that the treatment is influencing this blood pH factor that we're controlling for in the data table. So what about that? Well, that's a slightly different causal setup. The treatment causes this factor pH. The pH has an influence on the outcome, as does the treatment directly. So in a sense, the whole effect of the treatment it flows two ways. And if we were to control for pH, we would be cutting out the effect, one of the ways in which the treatment causes the outcome. And that's bad. We would be actually ignoring some of the effect of the treatment. So in this case, going back, it would be wrong to control for pH. And in fact, we should probably conclude that treatment B is better. What the data tells us is that you might interpret it that treatment B more often causes this low blood pH, and that in turn causes a higher success rate. And sure enough, treatment A has some other effect that's actually better than treatment B, but the dominant factor is treatment B causing blood pH and producing the better outcome. So again, there, just looking at the data, it's not clear whether to control for variables like this or not. And depending on whether you do or not, you decide that one or the other treatment is better. And the only way you can really figure out what's what here is to, well, maybe draw a causal model and also compare it to what you know to be reasonable causally in the real world. You have to appeal to some outside information to pick which one's correct. So the resolution of Simpson's paradox is it depends. Whether you want to control for the variable or not, it really depends. For the third example, which is Berkman's paradox, the causal model is something like this, that the axle ratio and maybe the carburetor count does influence the number of cylinders in the engine. I don't know if that's true, but let's assume it is for now. And there is no correlation between these two to begin with, unless you do control for the number of cylinders. Then suddenly this spurious correlation pops up. And if you're able to reason out this causal model from what you know about how the world works, then you can decide which of these two pictures makes sense. So the correct answer here was these two things are not correlated. That's the right answer. They're not actually correlated. And controlling for cylinders as we did and when we split them apart was a mistake. It created a false correlation where there really was none underneath. So once again, deciding between two interpretations of the data that seem to be both arise from the same data, we had to appeal to a causal model and to notions of how we think the world works. And once we did, it was clear what was going on. We knew what to pick. So if you like this sort of thing, and I do, let me recommend a book. It's called The Book of Why by Judea Pearl. Judea Pearl's long been associated with graphical models and causal reasoning. And the book is, it's a good book. It's a summary of a lot of his work and a reintroduction to what he calls the do calculus. It's additional tools for reasoning about causation from data and doing it correctly. So the do calculus is, I guess the fundamental insight is that these conditional probability statements we often are used to making or taking out of data are not actually equivalent to statements about what happens when we intervene in the world. So I may find from looking at historical data that days where it was raining seem to be the days I carried an umbrella, right? That makes sense, that the probability that I carry, the probability that it's raining does actually increase when on the days I observe that I've carried an umbrella. But that doesn't mean that just because I go out and carry an umbrella that it's going to make it rain or increase the chances of rain today. That is, it's the probability that after actually intervening in the world and changing X, the Y goes up is not necessarily the same as what I observe simply from historical data. And that makes some sense. There is a difference between saying that something's correlated and that going forward, one actually causes or controls the other, right? We've seen how that works. But just because we've introduced this new syntax doesn't mean we can do anything useful with it. And most of the book has to do with what the properties of this type of expression are. What you can actually say about interventions, given that we can't actually observe interventions from data directly. All we can observe are these sort of conditional probabilities. So he goes on to give a pretty interesting example about smoking. So it took a long time, but eventually the United States, decided that smoking caused cancer and needed to be regulated and labeled. But it wasn't clear for a long time what the causal link was. For example, was there actually a link between smoking and cancer where it was pretty clear smoking caused tar to build up in the lungs, and but people weren't sure whether it was the tar then causing the cancer and therefore this being the mechanism, or whether maybe there wasn't some other confounding factor, like some genetic predisposition that made people want to smoke, but also made them, unfortunately, get cancer at a higher rate as well. So even though you could observe from the data that this was a possible causal model, it wasn't clear that it wasn't being confounded by some invisible and unobservable genetic factor, at that time unobservable genetic factor. And this is what unfortunately caused the debate to take so long, because people just simply couldn't find a way to reason from the data about which of these two worlds was true, and couldn't decide that this was the actual world we were in and that therefore we had to do something about smoking. Now, I don't have room here to go into all the details, but you can, as you can imagine, work out a simple causal model here. And then, with the help of this do calculus, and we won't go through the derivation here, transform the desired statement, what's the probability of getting cancer if I intervene and I start smoking, into statements that only rely on conditional probabilities observed from the data. So there's only about 3 axioms to his do calculus, and they take a little bit of getting used to, but the good news is there are some mechanical transformations you can make to take out the do operator from an expression you want to evaluate, and ultimately cast it just in terms of things that you can evaluate and interpret. So one of the most interesting passages in the book is applying this process to actual data in the history of smoking and showing that this is roughly what researchers finally did in a different form to conclude that, yes, we do believe there is a causal link between smoking and cancer. So as I'm bringing it to an end here, what I want to reiterate is, well, number one, if you're new to data science, there are unfortunately things you don't know. So there are a couple of different pitfalls you need to be aware of when you're drawing conclusions from data. We live in a world where it's really easy to take data and apply a black box model to it and get an answer that may even seem consistent with some interpretation and stop there. But we have to back up and think, what else could this data and this interpretation be consistent with? Is this the only explanation, or am I actually running into some subtle paradoxes here, like Simpson's paradox or Berkman's paradox? When we interpret data and we interpret models, we are implicitly bringing a causal interpretation to it almost all the time. We're trying to draw causal conclusions from data and models that aren't necessarily directly giving us causal information. And sometimes that's actually valid. We get away with it. A lot of times we do, but sometimes it's not. So it's worth thinking about what assumptions you are bringing, what causal assumptions you are bringing to the data, and what other causal models could be consistent with the data. Probabilistic graphical models, the directed graphs I was showing, are a whole interesting field that do help reason about these relationships. You can appreciate that in these examples with 2 or 3 variables, it's pretty simple to just think through what's a confounder and what the effect is. But once you get to 5 or 10 or 20 variables, it gets really hard. And fortunately, there's a whole other set of tools you can use to reduce and simplify these graphs when you're trying to reason about them. And finally, for the truly interested, there is a whole do calculus from Judea Pearl and others that can help you correctly make statements about causal effects from data if you really, really want to get it right, given a graphical model. Worth reading. So we have just about 5 minutes left. I did want to leave some time for questions or comments or maybe objections from people who may be doing data science and have encountered these, and we'll have some other war stories to share as well. Question here?
Great talk, thanks a lot. I heard about this concept a few years ago from economists and social scientists. I used it a lot, and I read the book and thought it's great. And then I've seen a lot of machine learning projects in my daily work, and no one is using it, even though in the area I work, in retail and online marketing, you deeply want to know about causation, and you would like to get rid of A/B tests maybe and understand counterfactuals. So do you have an explanation why it's not used more widely in practice? Is it just ignorance or blind spot, or is there a more fundamental reason?
So why don't people think about causation and maybe formalisms like this more?
Yeah, and use it more in practical industry machine learning projects.
Sure, I think it's probably, it's not trivial. It's a little bit complicated. It's a little bit new. I hadn't come across this until I read the book, to be honest. I think in some cases we implicitly, we get away with it, I'll say. So we do conflate the idea of, we're reading off the data probability of y given x, and we're assuming it's really probability of y given that we've intervened and changed x. But those actually work out to be about the same anyway. And in some situations, they are equal, given some assumptions. So in a lot of cases, I think that people's intuition that what they're measuring is measuring a causal effect is probably correct, or roughly speaking. And so we get away with it. It's in cases where some of those other effects that we're not quite thinking too hard about make those things very different, that we get into trouble in subtle ways. I mean, I think it's obvious from maybe that first example that one of the 2 conclusions was obviously correct and obviously wrong, but it quickly gets hard to figure out when you get complicated. So I think we do need to use these tools more.
Hello. Thank you very much. I have a question. I think what you presented links very much to my concern about how we incorporate pre-existing knowledge into data science projects. Do you have any experience that you could share with us? Thanks.
So how do we incorporate pre-existing knowledge into data science projects? So yeah, you're right. So let me back up here. So this is an example of, in a way, knowledge. It's outside of the data. This is a causal model. And I think maybe this talk is exactly an example of that. I have a bunch of data, but to interpret it, I need to bring outside domain knowledge. And I think sometimes we're maybe play fast and loose with that, but there are formalisms like this. And these are the kind of things that a doctor would have to help you develop, right? Not just a data scientist. But it's essential to interpret the data correctly. So I think most of the time when we say how do we bring additional knowledge, and we're asking how to bring additional data in, and that's just a data problem. That's just a data science problem. That's a modeling problem. But I think the interesting difference here is this is a way to bring in a really crucial element, which is causal information. And that's what this tool is. It helps you reason about and add to the modeling process.
So thanks a lot for the talk. And so over here, you're kind of manually modeling your knowledge in the situation about the causation of the different effects. But are there any automated algorithms or any mechanisms through which the algorithm can detect this kind of a structure from the data itself?
Let's see, so can you come up with this just from the data? Yes, you could from the data read off what things the data says are dependent or conditionally dependent or independent. I don't know how practically useful that is, because your data, you might find something is very weakly correlated, and you've got to decide whether you think there's no relationship there or not. I think there's certainly ways to decide whether a model is inconsistent with the data. So for example, if I had in here that axle ratio and carburetors are uncorrelated and the data says they clearly are, then I could conclude this model is not consistent with the data. I don't think there's really a way to go always from the data to one or more causal models that could have generated it, just because the data itself is noisy, maybe. It's an interesting question.
Actually, there was a Causal competition where we showed that it could predict whether X implies Y or something.
Yes, there are tools for trying to decide whether A causes B or not. They're kind of approximate, but yeah, that's a more advanced topic. But yes, I think the answer to your question is maybe the point is you can't necessarily read these off the data, or you can sometimes read multiple ones, causal models like this off the data, and it's hard to know which one's which.
Sorry, it was a question kind of related to the second last question about tools for deriving probability graphs, practical tools that are used in data science.
So the question is, what tools can you use to derive these models from data?
Exactly, yes.
Yeah, I think it's the same question. I imagine you can read off conditional dependencies and independencies from the data set. But if your data set's noisy, you'll rarely have zero correlation between variables. You'll have just small correlations. So I don't know, except in sort of artificial or very simple situations, whether you can read off possible dependency graphs from data. I don't think that works in practice very well. You could, however, given a model, decide whether it's consistent or not with the data you do have. So you could rule out some of these, just given data.
Hi, thanks for the interesting talk. Can you show the graph for your third unsettling example?
Let's see,
the one with, you mentioned, or there was this where filter, and there was 6.
Yeah, so
with this example, yeah. My question, in the initial scatter plot, what I see is that there are two patterns superposed. Yeah, this one exactly. And when they are superposed, they annihilate each other. So you don't get any pattern. You are not observing any pattern.
That's right.
But if you are filtering, if you know the threshold, which is 6 here, then you are able to observe the pattern. So now my question. Was it a domain expert who told you about this 6, or did you discover this with a data-driven method?
This was me just trying to find any example that roughly worked. So I was hacking my way through all the combinations of variables pretty manually to see something that was not correlated in the overall data set, but correlated once I controlled for one of the 2 variables. So as an example, 5 out of 10. It's not a super example. The more maybe simple, intuitive example, which I didn't have a chart for, is there's a common conception that when we're out there, when we're young, we're dating people, we either meet people that are smart or attractive, but not both at the same time. And why is that? Why is there this negative correlation between smartness and attractiveness? And well, I think the explanation is that there's a whole world of attractive and smart people, but you're probably not going to maybe talk to that bottom lower quadrant where that's neither attractive nor smart. And so amongst the world of people you'll date, maybe this is a bad example too, if you fit a trend line, it would inherently be negative because you've sort of, you've partly controlled for a confounding variable there. So in some sense, that's the same thing going on here.
All right, last question. Okay, thanks for your talk. So I'm a French data scientist. I'm the head of a team of 4 data scientists in a French company. With I for one, contrary to some of my colleagues, have quite classical training in statistics, and especially I'm really familiar with some methodologies for classifications like factorial analysis that French statisticians favored for a long time. And it's not much a question, but an insight I would like to have your opinion on. I observed and I tried to train my colleagues in a discipline that we shouldn't have the main goal of a scoring or a predictive analysis without a great care for analytical statistics, discovery of data, and especially the concern about mixing of different populations in data. That's something I experience obviously in marketing because there are a lot of different types of clients, but also in industry with data from machines, and today with in my current job with press articles. And so, do you think there is an ideal methodology to discover data, discover subpopulations, and that way confront those insights, those categories we discover with people from the job, people who have a natural common sense knowledge of those data to avoid those mistakes.
So is the question, how can we avoid these mistakes? Because data science is, unfortunately, a lot of engineering, so a lot of software engineers like me are doing data science. I don't have a great answer to it other than to say we need to raise awareness of these issues. Just throwing auto ML at data is powerful, but it's not the last step. You need to have some sense checking about what conclusions you're reaching from the data.